In 1943, German engineers got their hands on an enemy engine that would reveal an uncomfortable truth. What they discovered would change their understanding of the aerial war forever.
The year was 1943, and the skies over Europe were painted with contrails of daily combat. On a cold November morning, a Royal Air Force Spitfire Mark IX crashed in occupied France after being hit by flak near Abbeville. German recovery teams arrived within hours, not to bury the pilot, but to salvage something far more valuable: the Rolls-Royce Merlin 61 engine, still intact within the twisted fuselage. This wasn't the first Allied aircraft to fall into German hands, but it represented an opportunity. At the Daimler-Benz testing facility in Stuttgart, Chief Engineer Fritz Nallinger had been authorized by the Reichsluftfahrtministerium to conduct comparative analysis between captured Allied engines and Germany's own power plants. The Merlin, legendary for powering both Spitfires and the new American P-51 Mustangs, was particularly intriguing. German intelligence knew the Merlin's reputation. British and American fighters were increasingly outperforming Luftwaffe interceptors in range and endurance. The question wasn't about horsepower. The Daimler-Benz DB 605 produced comparable output at 1,475 horsepower. The mystery was operational. Why could Allied fighters escort bombers deep into German territory while Bf-109s struggled with fuel limitations? The captured Merlin was transported to a secure hangar, where German technicians carefully disassembled it. What they found was a 27-liter V12 engine, significantly smaller than their own 35.7-liter DB605, yet producing similar power. The engineering philosophy was immediately apparent. British designers favored high rotational speeds, up to 3,000 RPM, while German engines operated at a more conservative 2,800 RPM with larger displacement.
The examination revealed fundamental differences in design philosophy that reflected each nation's industrial capabilities and strategic priorities. The Rolls-Royce Merlin employed a traditional carburetor system with a two-stage, two-speed supercharger, a complex arrangement that required precise manufacturing tolerances. British engineers had mastered the metallurgy needed for components that could withstand extreme thermal stress at high RPM. In contrast, the Daimler-Benz DB 605 utilized direct fuel injection, a technology German engineers considered more advanced. Each cylinder received fuel directly into the combustion chamber, allowing inverted flight without fuel starvation, a significant advantage in dogfighting. This system also theoretically offered better fuel atomization and more precise mixture control. Yet size told a different story. The DB605's 35.7-liter displacement dwarfed the Merlin's 27 liters, a difference of nearly 33%. German designers had pursued a long-stroke configuration, with pistons traveling greater distances per revolution. This approach typically enhanced low-end torque and was thought to improve efficiency. The Merlin's over-square design, bore larger than stroke, prioritized high RPM power delivery. Testing procedures at Stuttgart followed rigorous protocols. Both engines were mounted on dynamometers capable of measuring power output, fuel consumption, and thermal efficiency across various operational conditions. German technicians ran each engine through identical test profiles: cruise power at 15,000 feet, combat power at sea level, and maximum emergency output. Fuel flow meters recorded consumption with precision down to milliliters per minute. The British engine's two-stage supercharger particularly impressed the German team. At altitude, where air density decreased dramatically, this system maintained manifold pressure more efficiently than the DB605's single-stage unit. This translated directly into sustained high-altitude performance, crucial for bomber interception and escort missions.
If you're still watching, you're witnessing history itself. Subscribe for more untold stories from World War II. The data from Stuttgart's testing facility arrived at the Reichsluftfahrtministerium in early 1944, and the numbers were undeniable. Under cruise conditions at 15,000 feet, typical escort altitude, the Rolls-Royce Merlin consumed approximately 340 liters of fuel per hour while producing 1,200 horsepower. The Daimler-Benz DB 605, generating equivalent power at the same altitude, consumed approximately 486 liters per hour. The calculation was stark. The German engine burned 43% more fuel for comparable performance. This wasn't a minor discrepancy. It was a fundamental efficiency gap that translated directly into operational range. A Bf 109 G6 carrying 400 liters of internal fuel could sustain combat operations for roughly 50 minutes at cruise power. A Spitfire Mark 9 with 386 liters could operate for nearly 70 minutes under identical conditions. German engineers scrutinized every variable, seeking explanations. Combustion chamber design revealed significant differences. The Merlin's hemispherical chambers promoted more complete fuel burn, while the DB 605's chamber geometry, optimized for direct injection, showed areas of incomplete combustion at certain mixture ratios. Thermal imaging during testing showed the German engine running consistently hotter, indicating energy losses through cooling systems. The two-stage supercharger's efficiency advantage became particularly evident at altitude. The Merlin's intercooler between supercharger stages reduced intake air temperature by approximately 50 degrees Celsius, increasing air density and allowing more efficient combustion. The DB 605's single-stage system lacked this intermediate cooling, requiring richer fuel mixtures to prevent detonation at high boost pressures. But perhaps most revealing was the mechanical efficiency data. The Merlin's higher rotational speed, initially seeming wasteful, actually reduced friction losses per power stroke. Faster rotation meant shorter combustion duration and more complete energy extraction from each fuel charge. The DB 605's longer stroke meant pistons spent more time under pressure, increasing friction and heat generation. For Luftwaffe strategists, these numbers explained persistent tactical problems. American P-51 Mustangs, equipped with the Packard-built Merlin V-1650, could escort bombers from England to Berlin and back, a round trip exceeding 1,800 kilometers. German interceptors, forced to scramble, engage, and return before fuel exhaustion, operated under constant time pressure.
The fuel efficiency gap transformed abstract engineering data into concrete battlefield advantages. By mid-1944, as Allied bombers penetrated deeper into German territory, Luftwaffe commanders faced an impossible equation. Messerschmitt Bf-109s and Focke-Wulf FW-190s, both powered by variants of the DB-605 and BMW 801 respectively, required forward air bases to intercept bomber streams effectively. But forward deployment created vulnerabilities. Airfields needed fuel depots, ammunition stores, maintenance facilities, all targets for Allied fighter bombers. The Merlin's efficiency allowed P-51 Mustangs to loiter over German territory, hunting for Luftwaffe fighters attempting to reach their own bases. German pilots increasingly found themselves in fuel-critical situations, forced to disengage from combat or risk running dry. Combat reports from 1944 revealed this dynamic repeatedly. On March 6th, during big week operations, Mustangs from the 4th Fighter Group engaged Bf-109s near Brunswick. German fighters, already at the limits of their combat radius, broke off after brief engagements. American pilots, with fuel reserves allowing another hour of operations, pursued aggressively. Multiple German aircraft were forced to crash land short of their bases, fuel exhausted. The strategic implications extended beyond individual engagements. The United States Army Air Forces calculated that each P-51 sortie from England to targets deep in Germany consumed approximately 1,200 liters of fuel round trip, including combat reserves. A comparable Bf-10-9 mission from a forward base consumed proportionally more fuel for far less operational time over the target area. German attempts to compensate proved inadequate. Drop tanks extended range but compromised performance and required jettisoning before combat. The DB-605's direct injection system, supposedly more efficient, couldn't overcome fundamental thermodynamic disadvantages. Engineers proposed modifications, improved supercharging, revised combustion chambers, but wartime production constraints and material shortages prevented implementation. By late 1944, the Luftwaffe's fuel situation became critical. Synthetic fuel production from coal, never sufficient, declined under Allied bombing. Available aviation fuel was rationed strictly, further limiting already constrained operational ranges. The Merlin's efficiency, irrelevant to individual dogfights, had become strategically decisive.
The Rolls-Royce Merlin and Daimler-Benz DB 605 represented more than competing technologies. They embodied different industrial philosophies that shaped post-war aviation development. The Merlin's production ultimately exceeded 168,000 units, manufactured in Britain, the United States, and Canada. Its design principles influenced decades of piston engine development, particularly the emphasis on high specific output through efficient combustion and sophisticated supercharging. The DB-605's direct fuel injection technology, despite its wartime limitations, proved prescient. Post-war aviation universally adopted fuel injection for piston engines, recognizing its precision and reliability advantages. German engineering data captured by Allied technical intelligence teams accelerated this transition. Ironically, the technology's potential was fully realized only when combined with Merlin-style efficiency improvements. Perhaps the most striking legacy emerged in post-war Spain. The Spanish Air Force operated both captured Bf-109s and Hispano Aviación HA-1112 Buchones, license-built Messerschmitts. Original DB-605 engines, worn out and irreplaceable, were replaced with surplus Rolls-Royce Merlin 500 series engines in the early 1950s. German airframes, British engines, operational necessity transcending wartime rivalries. These hybrid fighters flew until 1965, outlasting most pure German designs. Pilots reported the Merlin-powered Buchones as more reliable and longer-ranged than original DB-605 variants, a final testament to the British engine's efficiency advantages. Some aircraft appeared in the 1969 film Battle of Britain, representing both sides of the conflict. German airframes, ironically powered by the engines that helped defeat them. Modern analysis using computational fluid dynamics and advanced thermodynamic modeling has validated the 1944 German test data. The Merlin's efficiency advantages stemmed from integrated design optimization, combustion chamber geometry, supercharger staging, and thermal management working synergistically. The DB-605, despite individual advanced features, never achieved comparable system-level efficiency. Aviation museums across Europe and North America preserve both engines. At the Royal Air Force Museum Hendon, a cutaway Merlin displays its internal complexity. In Munich's Deutsches Museum, a DB-605 section shows the elegant simplicity of direct injection. Side by side, they represent not victory or defeat, but the relentless engineering competition that drove wartime innovation. The aerial war wasn't decided solely by pilot courage or tactical doctrine. Engineers, transforming thermodynamic calculations into strategic advantages, shaped outcomes as decisively as any battle. Fuel efficiency, unglamorous, technical, easily overlooked, proved as war-winning as firepower or speed.
What's your take on this engineering rivalry? Did the Merlin's efficiency truly decide air superiority, or were other factors more important? Share your opinion in the comments below. If you want to discover more hidden engineering secrets that decided World War II battles, subscribe to Archivos de la Segunda Guerra Mundial. Hit that notification bell. Our next documentary reveals something even more surprising about WWII technology. The war in the air was won in workshops and testing facilities as much as in the skies, and there are dozens more untold stories waiting.